Hello everyone, do you hear me? Do you hear me now?
Yes.
Okay, thanks. I don't know if I speak at this volume, if it is okay for you or it is
Seems fine to me.
It's fine, okay, thanks a lot. Okay, so let us start today's lecture. This is on the perceptron and the neural networks. Let me just share the screen here. Okay. Okay, so in general, we're going to focus at the end of most of the lecture on neural nets, but let's say as a historical introduction to that, we will try to discuss first the perceptron model, which is historically considered as the predecessor of the neural network, and but the perceptron is still a linear model, right? And of course, the neural nets is just trying to make a model more flexible, non-linear, and then we will see how this works. But perceptron has many of the elements that neural network has. So let us introduce the perceptron first. So yeah, so originally is originally conceived for classification for binary classification task. So it's like the original idea of the perceptron, and then the idea is to model the output given some input of a, let's say in general, a nonlinear function, but we'll see which function it is, of a linear combination of inputs. And when I say linear combination of inputs, remember that this guy here, which I consider my input, may be in general a transformation that you have done has a pre-processing of your data set, right? So it is a linear combination of the input in phi space. And remember that we are always thinking of this object as the thing that defines the probability for class, let's say class 1. I'm in a binary context. So this probability for class 1 given some input and some parameters, okay? However, in the case of the perceptron here, there is a specific form for f of a. It's very simple. It's just +1 if the argument is larger or equal 0 and -1 otherwise. And then because of this choice, then it is convenient to parameterize the data set, to parameterize the labels of the data set as for a point I will be either -1 or 1. So previously, in the context of probabilistic classification, as we saw the other day, and also this is true in the context of neural networks, it is more convenient to work in the 0-1 parametrization, but specific to the perceptron, it is more convenient to choose this parametrization of the label instead, and this is just because of this choice of the function. Okay. So then you have a data set, which can be d-dimensional, and then you have for each point you have -1 or 1. So a graph that represents this model can be actually drawn like this. So imagine I have some dimensions, phi 1, phi 0, sorry, phi 1, phi 2, phi d in general. I have d dimensions in my input in phi space. Sorry. Then what you do with all these phis is to combine them in order to form the argument of your function. So then you just compute the function, and the way you combine the argument is just by connecting these points to this argument. So this is just W0, W1, W2, WD. Okay. And so this is actually reminds you quite a lot the structure of a neural network. Reminds, but also logistic regression, which, if you remember from previous lectures, I don't know if it was a lecture 4, probably. Let me just go back to lecture 4 at the end of the lecture. Logistic regression is that, right? You remember this expression? It is exactly that. This a nonlinear function is another nonlinear function, not this one, but it's a nonlinear function of a linear combination of the input. And this is exactly what is happening here, right? So also logistic regression and the perceptron, they may have the same like graphical, the same graph, if you want. Okay. So now the task here is to train. So to train the perceptron model. Which means to find the parameters, of course, this W, the optimum parameters, right? That minimize some function. So let's minimize some cost function and find the parameters that minimize this function. So, however, the thing is that the first cost function that would come to your mind after seeing these lectures, let me see, sorry, there is a question. The first function that comes to your mind may be, for example, the cross entropy. So imagine that you have a cross entropy, and in the case of the cross entropy, which was already shown here in the case of the logistic regression, something like this, but for binary classification. However, you see that when you have this cost function, sorry, the idea is to differentiate the cost function with respect to the parameters, and at some point you need to take this derivative. So this is problematic. So cross entropy is problematic because it involves derivatives of f with respect to a, with respect to its argument, right? When I do the chain rule, but this is discontinuous because of the very definition. Discontinuous because you see that this function is just this or this, right? So if this is one, this is one, and this is minus one, and this is a. So this is not a convenient function to minimize. So instead, what the perceptron is doing is to consider the following plus function. So this is a function of omega. And then there is a sum here. And then I will tell the sum is over what of this ti. Ti, remember that this is the label of each point. But I will sum only through the points which are misclassified. Okay, I am not considering the points which are correctly classified, but only the ones that are misclassified. So why this class function? So note that, let us understand this class function for a second. So if ti is +1, then a correct prediction has this, right? Larger than 0, because I'm saying that if I have larger than 0, I have +1 here. So the argument of f should be larger than 0. And if, on the contrary, this is -1, then a correct prediction has the opposite. No? So combining these two, this object is always like this for all points which are correctly classified. No? Which means that misclassified points they have this smaller than 0, and then each of these terms are negative. So with this negative sign here, the whole thing becomes positive, and then I can a minimum is well defined. Okay. So which means that this thing is positive. Okay. And then I can minimize it. Please, if you have any question or anything that that you note that I say or that you don't understand or is incorrect, please just say it and don't write it in the chat, because then I'm usually not following the chat. So then how to minimize this? So interestingly, back in the 60s, I think this is a model from the 60s, they use a variant of what is called stochastic gradient descent. Which is actually today is one of the most popular variations of it, improvements of it, but everything is based, I mean, most of the optimization in machine learning today, in numerical complicated models like neural networks, they use stochastic gradient descent today. So let us open here a parenthesis to explain what gradient descent is. And then we continue with the perceptron. So gradient descent is an iterative algorithm. So this is an iterative procedure or algorithm to find the minimum of a function such that, so for minimizing or for optimizing, let's say, for optimizing a function, such that at iteration tau plus 1, the parameters are updated in the following way. At iteration, and then in the machine learning jargon, this is epoch also, but this is just an iteration of it's an iterative procedure. This is just updated in the following way. So it was the previous point, I mean the value in the previous iteration, minus some prefactor here times the derivative of the cost function with respect to W. So this guy here is the cost function. And this prefactor here is called the learning rate. So the idea, if you want, is the following. So let me write something, and then I put a figure because it's probably better. So imagine that you have a two-dimensional parameter space like this, okay, with contours of values, let's say. And the idea is to start with a random point here and approach the minimum iteratively, right? So this is more or less the idea, depending on the learning rate, of course. So let me share a picture that I think it was shown in the first lecture. This thing here. Okay, something like that. So here the idea is that you start, let's say you start here somewhere or here, and then you slowly you move towards a minimum here, let's say, right? So you go down the hill. So you do this descent, right? By computing at each epoch, by computing the improvements or the updates of the parameters in this way. Of course, if there is a unique minimum, then the algorithm is working no matter where you start. However, here the problem is problem with local minima, because just by doing this thing, it is not enough to make sure that you don't go to a local minimum, but what you want to do in general is to go to the global minimum, right? Okay, so depending on the learning rate, so let me put it here. So depending on the learning rate, sorry. Then you will succeed or not in finding your minimum because of the following. Imagine that you have a large learning rate, and then if your function is something like this, and then you start here, if your learning rate is too large, then you may just do this thing here, and then you may miss your minimum. You probably miss the minimum. And if it is too small, then you won't miss your minimum, but you are wasting a lot of time by doing small steps. Okay. And then you may waste a lot of computational time on that. So this is costly. It's not costly. It's I mean, long training. It's a too long training time. So a priori, this is something that you should optimize. This the value of the learning rate, and so the most simple form of a learning rate. So eta can be a constant for all epochs, for all tau, let's say. But there are some implementations, and typically the out-of-the-box implementations that you find in the market of neural nets, they use some adaptive value for the learning rate, but sometimes, for example, they do something like proportional to the epoch. So it is something that decreases as you move forward into the training in the iteration of the epoch, right? So this is really a hyperparameter of the model that should be optimized. Okay. Now to close with this parenthesis, the stochastic version of it, then stochastic gradient descent. It is a way to approximate the whole object. This is the whole derivative here, the cost function here. So remember that the cost function in general, or it's quite typical to have a cost function which is of this form, 1 to n of ci w. Remember, so the cross entropy, for example, is just a sum over all the points in your training data set. And so this thing is expensive for large data set. So you may have million points, let's say, no? In big data applications, let's say this may be a problem, right? So a way to approximate this, so what the stochastic descent does is to say that that this derivative, which would involve differentiating all the terms, let's say, will be approximated by the derivative of a random point. Okay. So this is the idea, the basic idea behind the stochastic gradient descent. And then this is chosen randomly, right? So, and then you may say, what? So how come this can work? And the algorithm works because on average, so imagine I take the average of this quantity. Okay. If I take the average of this quantity, it means that I am summing over this quantity and I'm putting this, which is exactly the derivative of the total function, right? So the average behavior of this derivative of a random points chosen of these points chosen randomly that you take to approximate the whole derivative of your cost function will, in general, will on average tend to the same minimum. So if I do the same draw here, contours, etc., then what is happening with the stochastic gradient descent is that sometimes you go here, sometimes you go here, sometimes you even go backwards sometimes. But it turns out that on average, it is converging on average to the it's like these ants, right, which are having random walks, but the random walk is actually on average going to the correct direction. Okay, so this is the what I wanted to say about stochastic gradient descent. Is there any question on that so far?
I am.
Continue. Yes, please.
Yes, Jose here. I have two very simple questions. So one is on the normal gradient descent. So you say a cheap trick is that you make the step smaller as you increase the epoch. So this saves you from bouncing like crazy. This saves you from your large eta problem. But if you are going too slow, you keep going too slow. I mean, and even slower. So there's no measure against that, right?
So what you're saying is that by following this recipe, you get slower when the epochs are approaching. This is your point.
Yeah, I mean your plot where you wrote that is too small, right? If you readapt the learning rate and you make it smaller with the epoch, I mean you keep making it. I mean, it's only getting worse unless you put some stopping condition and you say, okay, if I.
Yeah.
So it seems you are only solving one of the two problems that you could find. That's my only question.
So I mean, corresponding to this choice, if I am trying to find the minimum of some function like this, then it's probably behaving something like this. Right, so it is doing big steps at the beginning, and then finding, if you want, the correct, more or less the correct minimum at the beginning, and then I don't want to miss it. I don't want to miss the minimum, so I go slower because I want to be more fine in my more precise in my estimation. But normally this happens once you are surely going to a minimum, right? I mean, of course, it slows down your computation at some level, but at least it is not as slow as this, because essentially most of the time you waste by putting a constant learning rate which is too small is that you waste a lot of time, like for example, going down this hill here. While if you do this adaptive method, then this hill you go down very quickly, and then at some point you start slowing down, but then you are already trying to prove the minimum. But at least you left the hill quickly.
Okay.
Yeah.
Okay, and now the second question. In this assumption that you can essentially approximate the derivative by a random point of the distribution, this doesn't depend on the shape of the cost function, or let's say how your data was given to you, because if the data is essentially independently distributed, right, you can say that this should be valid. But if there's some bias in the data, this is not something that you should be worried about.
As long as you can put your cost function in this form, which is typically happens. Where this come from? It is coming from the fact that this is the minus log of the likelihood, and the likelihood is a multiplication of probabilities, and because each of them are independent, this is your assumption, and then you can put your cost function, the total cost function has a sum on that. As long as you can put that, no matter the data set, of course, it depends on the data set, the performance of that depends on the data set. But I'm saying that this property, that this has the correct behavior, works just because you have this shape.
Okay, thanks.
Okay. So so if there is no more questions on gradient descent, let me go back to the perceptron. So back to the perceptron. Here, let's say that thanks to stochastic gradient descent, I apply that, and then I evaluate the update for the epoch or the iteration tau plus 1. I evaluate this. I put a learning rate. Yeah, right. This is going back to the perceptron. Why this? Because this is, you see, this is the derivative of my cost function. Where is the cost function? Cost function is here. So I differentiate with respect to W, and this is what I get. Okay. So then I can just do the following trick. So I just divide by eta on both sides. And then since the perceptron, since the output of f is independent actually on the specific value, or if you want this is invariant on the rescalings of the W, I can just forget about my eta and write this like this. Because f of a is invariant under rescaling of the W's. This is in this particular model, okay? No, this is not true in general. But in this particular model, this is true. Okay, so what this implies is that at each iteration, tau, you find a random misclassified point. So find a random misclassified point. And do the update as the following. So either you sum this because the point was belonging to class 1, which means t is 1 for this point, or t was -1, and then you need to subtract to the other class, okay? So with this method in iteration tau plus 1, the error will be smaller than in iteration tau. And why is that? It is because the following. So in iteration tau plus 1, I have this contribution to the cost function. So let me replace what is this. Let's say I have this Ti transpose times phi Ti. Okay, I'm just replacing by gradient descent what it was, and then this is just okay. I'm just opening here the parentheses. Ti minus. Let me put it downstairs here. Minus Pi transpose Pi. right? And note that this term here is positive because it is the same term squared, let's say. And since this is positive, then this, I don't want to write it again, but then this thing here is smaller than the first term. Okay, so you see it. So this is a demonstration of why, by following this strategy, every time you do an iteration, you get that your error function, your cost function decreases. So there is of course, you focus on a random point, on a random misclassified point, and by moving your decision boundary, you will see it. Thanks to this random point, you may actually misclassify points that were correctly classified before. Okay, so it is globally, let's say, it doesn't work for all the points at the same time, but on average, this is working because of something called the perceptron convergence theorem, which says that essentially that if data is linearly separable, then the whole process described above is guaranteed to converge in a finite number of steps. Okay, so let me just share with you this picture that I think I showed in the first lecture, but here trying to explain it. Yeah, this one. All right, so these are this is how this is a bishop, by the way. This is how the perceptron is working. So imagine that I start with a random vector. I start with a random vector defined by this black arrow. And if I have this black arrow here, then of course I am defining, I mean, the corresponding decision boundary is this one, right? So you remember that we said, I think we said at the beginning of the classification lecture that you have the weight vector, this parameter vector is actually perpendicular to the decision boundary. Now, the arrow points towards the points of class of the red class of red points. So the arrow should point towards all the red points. And if this is the case, then this red point here and this one are misclassified because it is on the opposite side of the decision boundary. So the way it is doing this is in the first iteration, I take a random misclassified point, for example, this one, and then I am adding this plus this, which is giving me this this result here. Sorry, yeah, this plus this, which is giving me, or minus this, sorry, is giving me this result here. And this result here defines a decision boundary. And this is like the result of my first iteration, so how it moved. Now I need to do the same. So I need to find another random misclassified point and then update again my weight vector. So let's think that it is this misclassified point. So this is the corresponding vector, the feature vector, or this phi I for the misclassified point. So I add it to this one, and then I get this one here, which is defining a decision boundary by which all the points are correctly classified. So in 2 iterations, this data set is in 2 iterations is correctly discriminated, right? So it's correct to separate it between red and blue. But this is more or less the workflow of how the perceptron is working. Okay. Any questions so far?
Why the error is perpendicular to the decision boundary?
I think we said, let me see if at the beginning of lecture 4, yeah, so, okay, so probably we didn't spend time on that. When you define a line, imagine you have this parameter space. When you define a line here, then what you see, let me see if I will probably, well, this is a good thing to do. Yeah, because I think we didn't then do it. So it's essentially it's a geometric reason, right? So the points on that line are such that you essentially realize this. So let me open. Let me put here some new page here. So imagine you define a line here, and then you have points on this line. So the equation for this boundary may be written like this, right? So this is the equation of that line, right?
Yeah.
Then you see it, because then you can express this as equal to 0.
Okay.
So then you have a scalar product. So this is telling you that this is perpendicular to the points of that line. Okay.
Okay.
So in the sense that I have. So let me see. Let me develop this more. So imagine take 2 points. If I take 2 points, then I have point A, which is x1A, x2A, and point B similar. And then I have, well, actually, a generic line doesn't have to be 0 here. It's C. It's some value, a generic line. But then I can do the following. For both points, I can do this. And since this is a constant, then I can exactly do the same with point B. Okay? Which means that I can express this as xa minus xb, and this is equal to 0. So this term here lies on the line, while this term here is perpendicular to the line. Okay?
Yeah. Okay.
Yeah. So yeah, probably I forgot to explain this in the lecture of Friday. Any other question? Okay, if not, then we move to, so let's move now to neural nets. But the idea here is to, as I was saying, to make a more flexible model. And so let me start. Let me start with a linear model. And a linear model that can be, for example, logistic regression, right? But so the output of the model, given some, just let me call the parameters now V. So this is just a function, a nonlinear function in general, of some linear combination of the inputs, right? And this linear combination of the input, let me write it in this way, from H1 to capital H, VH, and you have these phi terms here. So you agree with me that this is a linear model, right? At least in phi space. Okay, so then this is a generic function here. And actually, this is a generic function here. And actually, f of A is equal to A for regression problems. And this is what we saw, no? We saw like a basis, for example, if these guys here are powers of X, this is like a polynomial. And if it is a classification, as in logistic regression, then f of A is a nonlinear function. For example, the sigmoid, in the case of logistic regression, and then you interpret this as the at least in probabilistic interpretation, you interpret this as this. Okay. So if I want to have a more flexible model, then I am allowing for this guy to be itself not not a simple function of the input, but a nonlinear function of the input. For example, I have, let me express this phi as another nonlinear function g of a linear combination of the input. So these are weights, xd plus h0, let's say. So this is a nonlinear function, which is called also the activation function. And this is just, these are just parameters. I'm saying that for every phi h here, I have a function like this, where with different parameters, w, wh, which are the vector. So what I'm saying is this, wh is a vector with h components, let's say. Sorry, with d components. Is it clear? So the model becomes, now the following. Now I have two parameters here, w and v. So this is this first function here, but I am replacing now this part. So this is just h to capital H, vh of a nonlinear function g from d1 to d, and this is just the dimension of the input, hd, xd plus wh0 plus v0. Okay. And this is just a one hidden layer neural network. This is just that. Let me call these guys here z, h, and then I can represent this function. I can represent this model in the following way. So I start with all the inputs as before. So let me start with the x. So this here I have x1, x2, right? xd, because I have a d-dimensional input. And then from the x, I go to the z. By going to the z, I have, I don't know, I have a number of z here, z1, z2. I have capital H of them. And how do I go from x to z? Well, I connect through all these weights, right? So I am obtaining, if you want, all these z1, z2, all these is called, they depend on all the inputs, right? Like this. So, and now from Z, I go to the output, the output Y here. And also here, so what is the connection here? The connection here is, for example, WH, well, for example, this is W11, if you want. And this is W12, etc. Right? So in general, all these guys are WHD, DH, sorry, WDH. And somewhere here, I also have an intercept. I will put here H0, and this intercept is affecting all these ZH values, right? And then from going to Z to the final output, I need to do exactly the same, but with these weights and this intercept. So in general, I'm saying that all the sets are affecting the output, and these guys are the VH. Here, only VH. Sorry, 1 second. Yes. Estoy en clase ahora, perdona. Ahora. So then, and then I have an intercept down here, or I can put it here if you want. V0, that is also affecting the intercept. So this is like an graphical representation of this equation here. And this is also called feed forward. Feed forward. Neural net, in the sense that I go from the input to the first layer to the output. And if I have more layers, as we will see now, first layer, second layer, third layer, etc., and the output. So this is for regression, while for classification, so remember that for classification, the output is k-dimensional. So I have 3 k classes, and I am parameterizing my output as a vector, a binary vector of k components in this one-hot encoding procedure or parameterization. Right, and then I need something like this for each of the k outputs. So then I generalize this. Okay, I will have an output. So for K1 to capital K, let's say, this is capital K here. And then, so let me write it below. So I have for each of these k, I have the same thing. But now, instead of being v, a vector, it's just going to be a matrix here because I have k outputs. So I need a matrix instead. This is over d, hd, so this part is the same. And the intercept here is one intercept per class, let's say. So what I'm saying here is that, so this can be represented as, so if this is x1, x2, etc., and this is z1, z2, etc., then by doing this, etc., I need to connect now all the points of my hidden layer to 1, 2, and there are k of them, k outputs, and all of them will contribute to all the outputs, etc. Okay. And this is a representation of a neural network, one hidden layer feed-forward neural network that now is used for classification because I need k outputs on that. So let me introduce now some matrices just to try to write this in more compact notations. Let me take this. I will take this too. What do I do here? Copy. So this here, let me introduce now. Oops, sorry. A matrix Y, which is the matrix of all the outputs. And if it is a matrix of all the outputs, this is a matrix with dimensions n by k, because I have n points on k classes. Let me introduce now a matrix V, collecting all these guys here to be a matrix of h times k. This is the number of hidden number of units in the hidden layer times the number of outputs, and then I do the same for the intercept, similar to for the intercept, and with respect to the other weights, these w's here, I collect them in a matrix, which is d by h. The intercept, which is n h, and finally, of course, you know what is the output, the input, sorry, which is n by d. So by all these matrices, I'm collecting all these coefficients in a matrix. Then I am just able to write this thing as the following matrix notation. So this is all this is capital letters, right? Plus W0 times V plus the intercept, right? And so you know it works, right? So this is so this thing is n by d with d by h. So the whole thing here is n by h, and this here is also n by h. No? So and then whatever g is n by h. That I multiply this by something which is h by k. So then this gives me n by k, but this is also n by k. And of course, then the whole result is n by k, which is exactly dimension of the output. Is there any question so far? No. Okay. So if there is no questions at this level, we can make a break of 5 minutes if you agree, and so we come back at I don't know, 7 past. So okay, let's make it, because I need to do something now. Let's make it 10 past 12. Okay, so 8 minutes break.
Okay.
Okay, see you now. Okay, so let's continue. Let me start video here. So where were we? We
Just rewrote the.
right. So yeah. So exactly. So now let me go back to my notes. So this is a, let's say this is a one hidden layer neural network for classification, right? And now, what about a neural net with two hidden layers? So now, a neural net with two hidden layers. So of course, here you have a, in between, if this is the output, you have two columns of this here, and this is the input. And now you realize that you need another set of matrix, right? So this is the matrix of the from the input to the first layer, but now you need the matrix of parameters of the first layer to the second layer, right? Something like that. And then it is only in this architecture. Of course, there are many architectures now in the market, and every month you have a bunch of new architectures, let's say. But the idea is that only the last layer is connected to the output, right? So how would the model look? How would this look like? Is the following. So I have my matrix of output, or this is the output of the layer. So this is the first or the hidden layer connecting the last layer to the so connecting the last units to the output, and then I have one activation function, another activation function here, and now it's a function of the, let me put here W1 plus the intercept, and this is multiplied by W2 plus the intercept, and this is finally multiplied by V plus V0. Okay, so what I just did is just to replace here, I just replaced X by another thing which can be written like this. And then I just open a bit or increase one level of nonlinearity if you want. All right. And then so on. So I can add as many layers as I want, and then I can if fully connected, let's say, then it is just a matter of every time you see here an input, you write it something like that, and then you have W3, W4, etc. Right? Okay, so what about the activation functions? So activation functions here, they have been, for example, I can have the sigmoid for hidden layers, and then I can have the softmax that we just, I think in the lecture of classification we saw them for the output layer. Of course, if I have a classification problem with K classes, I better use softmax, right? So in general, there are many activation functions. So here I'm just showing two of them. So if this is 1, this is 0, and this is -1. So you know that this was the sigmoid, but I can also use the hyperbolic tangent here, and hyperbolic tangent here goes to -1 instead. So this is hyperbolic tangent. Okay, and this is A. So instead of this one, I can use hyperbolic tangent, etc. So there are, for example, more recently, a popular activation function is so-called rectified linear unit. Rectified linear unit is just the max between 0 and A. So rectified linear unit is just this thing. So let me put it in another color. Okay. So this is A, this is redo. This has also been used. And even a more modern is something which is called a variation of this, which is called leaky ReLU. And leaky ReLU is the same, but with some slope below 0. So this is leaky ReLU. Some slope to be defined, let's say. Small slope. So in general, you have tens of activation functions. You just need to go to Wikipedia, activation functions, and then you will see order 30 or so, which are valid actually. So all of them, all the activation functions, of course, it depends on the problem at hand, but give, in general, good results. Okay, there are problems with the hyperbolic tangent, or there are problems with sigmoid, which has to do with the fact that the gradients here are 0 in this part. But let's say that in general they work okay, and this is a result. This is a result of the following, which is the universal approximation theorem. Okay, so this is a very important theorem saying that a feed-forward neural net with a single hidden layer, you just need one level of nonlinearity, one hidden layer here, containing a finite number of units or neurons. This can approximate any continuous function, also real valued. Okay, so a nice function. Okay, so not a nasty one, but I mean any continuous function, let's say, even though it is wiggly or whatever, but it has to be differentiable, etc. Under my assumptions of the activation function. For example, the theorem was actually proven with the sigmoidal types functions. This is proven with functions which have the following behavior. This is one for when a goes to infinity, and 0 when a goes to minus infinity. So even though it was originally proven with that, then it works even if this is not the case. For example, ReLU is not a bounded function, right? ReLU is not bounded, like sigmoid or like softmax or tangent, hyperbolic tangent. This works equally well. So all this requires actually, that you have the following. So imagine that you have here a graph. So you have some function here that you want to approximate. All it requires is that you be able to put this in, to approximate your function with rectangles. Okay, this is the only thing. So if you are able to approximate the function with let's say geometrical figures, but let's say something which is similar to rectangle, then you are good to go. And what I'm showing you here, instead of proving mathematically this theorem, which is a bit too formal, let me just share screen here, and I will try to implement this graphically with some activation functions. So let me just go and share screen. So do you see this?
Yes.
Okay. Let me. Right. So the here idea is very, very simple, right? So I am just using a notebook to do the following. I am implementing. So first of all, I am just defining some linear space in X. So I am implementing here the ReLU. So ReLU is a function that is the max between 0 and some a. So here a, I'm just putting two arguments here in ReLU because depending on the argument, this will jump at one value or the other. So if I evaluate this function above, when x0 is 2, then it is jumping at 2, or if it is 2.5, it is jumping at 2.5, etc. So here I am trying to approximate any function with ReLU. So it's like a graphical proof of this universal approximation theorem with ReLU. So note that what can I do with these two ReLU? So note that if I take these two functions and I subtract one to the other, so if I now define something which is called semi-rect here, it is just, by definition, it's just subtracting two of these ReLUs. And if I do that and I plot it, I get this. Obviously, because this is 0 up to 2, then it starts growing until the moment where the orange function also starts growing. But since they grow at the equal rate, then I have a constant from 2.5 to the right. And then I have this blue. So this blue function here is the result of subtracting these two here. You see it? And then if I, instead of starting at 2, I start at 4 with the delta, because I have defined the delta here, which is the difference. Where do I jump? So if you want delta, gives me, if delta is very large, then the slope is smaller. If delta is very small, then the slope is more pronounced, right? So it's more 90 degrees. So by doing this, I am, for example, able to have graphs like this one, like the blue one and like the orange one. So what now do repeat the exercise and do what happens if I subtract orange curve to the blue curve. And then I have just written here a function that does precisely that. This is just with some prefactor giving me some normalization here. And just subtracting one function to the other, evaluated in two specific points. And when I do that, I get this, right? So let me execute this. So let me see if this works. Right, so it's like this. And then I am defining this rect, and then I'm plotting it. So imagine that, so I have this like a trapezoid, right? But if I, let me uncomment this line, which is exactly the same, but I have replaced the slope, no, the delta by half. So if I do that, you see that I get something which is more similar to a rectangle, right? And if I even go slower than that, it is actually a rectangle. So so then the final step here, is to add many of these rectangles. And if I add many of these rectangles, because each of them, they are centered at some value, each of them, they may have different heights, sorry, or different slopes here, or because they are actually trapezoid. Then I get something like this. I'm just plotting here the result of adding one of these rectangles or these trapezoids to, right? So I am adding all of this. And then you see it, right? So I don't need to continue here because it is just saying, that I can adapt any all of these rectangles in order to approximate any function I want. I can, one of them may be wider, maybe narrower, like taller or not, right? But you see that the combination of this plot is a combination of ReLU. It's nothing but a combination of ReLUs. So, and even a ReLU, which is not a bounded function, can do the work for you. Okay, is this clear? Is there any questions so far? Okay, so this is all I wanted to say about universal approximation theorem. Anyway, I mean, if you are curious, I invite you to go to the original paper, which is free online in the internet. Okay, so let's then go back to the notes. Stop share. And share here. So this is the reason why I was actually posing this question in the first lecture of saying this is probably, is this the universal approximator? Well, in general, no, but in many practical situations, yes. So you can approximate whatever function. You can approximate it with a simple hidden, neural network like this one. And of course, I mean, if your function is very complicated, you may need a lot of units in your hidden layer. And then it may not be practical to do this with this architecture or this form of the neural network, but then you may like have more layers. And if you go to more layers, you go deeper and deeper. And then, okay, you have other architectures like convolutional, etc. But let us do one more technical thing here before finishing, which is about training the network.
Sorry, Brian, I have a
Yeah.
question.
Yeah, tell me.
Like, suppose that you have, for example, a function that you want to approximate the logarithm of x, and it has a divergence. So then, I mean, you would need an infinite number of layers of neurons.
You want to approximate the log of...
Yeah, like one function that has a divergence at some point.
No, the thing is that, okay, this function is infinite for large x. But if now you're training input, I mean, the training points here have input covering a limited range on that, then a neural network can actually approximate up to the range.
Mhm.
So it is ensuring that you approximated with the values of that function covered by the range that you have done for training.
So the theorem says that the number of neurons has to be is finite. So this is a consequence of the range is also finite.
In practice, yes. No. In
Yeah.
practice, the range is finite. So when you give a numerical, you have some data on your computer, and then it covers some range, right? Even it can be very large, but I mean, X can cover many orders of magnitude, but at the end of the day.
Yes, but I mean the requisite has to be that the function is, I mean, has no divergence on this range, right?
I think so. Yes. Let me. Yeah, I think this is true. I'm trying to see if I have here the paper, but yeah, I don't find. I may need to search for it, but yeah, I think this is true.
Okay, thanks.
Yeah. Okay, you said any other questions so far? Let me search one moment. I thought I had it here, but no, I need to search for the paper now because I thought I have it at hand in my file, but I don't find it now. But it should be finite, the function within the range of the training. Otherwise, you may need of course, you may need an infinite number of neurons, probably. Yeah. Okay. So what we're doing now, we're like seeing how the network is being trained. So what you do is, as usual, you find optimal weights. Or matrix of weights that maximize the likelihood or minimize the cost function. And let us work here in the context of classification, where I have the cross entropy. Let me write the cross entropy again here. So I will write it like this, but so let me think of this for a second. Now I will change, but let me think for a second of a function of a function of weights and collect all these weights in a vector, just to write this equation. To k to n of tik log of the output. And let me call this just y ik. Okay. This is the cross entropy written in this way. So I am just a sum over points and over classes. And then this output here, this function is given by neural network. So let me put here sigma I, because this is the output activation function of sigma, just to differentiate it from sigma. And I have only one hidden layer here. All these guys are matrices, which is nothing but I can just write it like this one, because I have called Z to all this part. Okay. So then I have let me consider that this is a sigmoid and that this is softmax, for example. And remember what was a sigmoid? So the sigmoid this was like this, and
Excuse me, in the rewriting of that last one, wouldn't it be B sub-zero instead of W sub-zero?
Yeah, sorry. Yeah. Too fast. Yeah, thanks. So what I'm saying is that the sigmoid is very convenient because the derivative of the sigmoid with respect to the function, to the argument, can be rewritten as sigmoid times 1 minus sigmoid. So when you use the derivative of this, you realize this. Okay. And for a softmax, which was written in this way, e to the ik divided by the sum of e to the ij, the derivative of the softmax with respect to some j here is equal to softmax of k, 1 minus softmax of k, of course, with the Kronecker delta, which is can be written as k minus like this. Okay. And then with this, let us start differentiating. So what is the derivative of the cost function of the cross entropy with respect to the intercepts of the last layer? So I'm applying here heavily the chain rule. So this is just minus the first sum, and the other sum I am just putting a k prime here because k is already reserved as an external index. So by following the definition of cross entropy up here, I have this. Then I need to differentiate this with respect to with respect to b0 with respect to the last intercept. So, but this is a logarithm. So differentiating a logarithm, then you have 1 over ik prime d ik prime v0k. Okay. So this is just that. Then rewriting this, but then I use the fact that this is the derivative of a softmax, because y is a softmax. Then this is just the function itself times k prime minus ik, and the chain rule is just to derive the argument of the softmax with respect to the parameter I am trying to estimate here, but this is 1. This guy here is 1 because this is the intercept. So this is 1. So I am able to rewrite this, and in this way. So you see that this guy is cancelled here. So tik times this, which is the same as k of tik tik prime times yik minus sum of I tik. Okay. I'm just opening the sums. But then this is the sum over k prime is 1 here, because this doesn't depend on. So what I'm saying is this yk times the sum over k prime of tik, but this guy is 1 as well, because it's for a point, all the classes, and of course this is a binary vector, so the sum is 1 minus the other term tik, such that at the end of the day I have the sum over I of yik minus tik, which I can in a compact way say this in a matrix form. Okay, the ik element of this matrix subtraction, and this is something that we will use tomorrow in the hands-on session. So now compute with respect to, so next let's compute this with respect to not the intercept but the matrix V itself. But we have done some work above, so this is just the same sum here. Tik k prime minus yk. So I mean, but with the difference that now you need to differentiate the argument of the softmax with respect to this. But you see that this is just ZIH, which is the units of the hidden layer. So what I'm saying then is that this can be rewritten as the sum ik minus tik times ZIH, which can be, so then I can say that in a compact form, the derivative of the cost function, this cross entropy, with respect to the full matrix V, by looking at the expression above, this is just this Z transpose Y minus T, right? And this is also something that we will use tomorrow. Now we have 2 more to go, but the last one is very short. But this one is a bit different. So now, what about derivative with respect to the matrix of weights connecting input with the first hidden layer instead? So let me just write it. I'm not showing all the lines, but I would write the first line at least. Yik. Then I need to derive again, so this goes away, this cancels, 1 minus yik. Now that what you need to do is to have the derivative with respect to that w. So in the chain rule, I differentiate with respect. I differentiate the argument of the softmax with respect to ZIH and ZIH with respect to W08. So this is the intercept of the inner part, right? And while doing this can be written as, just jumping one intermediate step here, yik, vhk, zih, 1 minus zih. And this can be written in a matrix form like this. E minus y ik matrix V transpose kh plus times the rest. So there is this product, which is not a matrix product, but this an element by element product, if you want, which is the following. So this part is the same. So y minus t times V transpose, and this is the element by element product Z, and element by element product of 1 minus Z. And the whole thing has elements IH. I don't know, probably mathematicians, they call this the Schur product. But this is just element by element. Element by element. Okay. And finally, the only thing that is left is the derivative with respect to the matrix that multiplies the input. And when you do something very similar to what I did with the intercept, you get this y minus t vt Schur product z 1 minus z, I mean unity, so minus z ih, but now multiply, because I mean this is the derivative with respect to the coefficients multiplying the input, and then of course you get the input here. So this can be written in this notation. T dt. Okay. So these expressions, this one, and the other ones, this one and this one, we are going to use tomorrow in order to train from scratch a neural network. It is just that Python allows you to do it in a very compact way, actually in a matrix way. So you don't need to do this this long product here, element by element, but it is possible to do it at this level, let's say, and this is quite convenient. But then what is next? So now you have defined all the derivatives of the cost function with respect to your parameters, and now what you can do is that you can, of course, update your parameters iteration by iteration or epoch by epoch. You update the parameters by this learning rate times these derivatives here. This is one and the other one, okay? And this is iteration by iteration how these matrices of weights are being updated, and at the end of the day, hopefully, you get a good minimum. So is there any question on that? Okay, the lecture stopped here. So there are some minutes left if you want to pose any questions regarding this lecture or any other issue.
Brian, as it was a question,
yeah.
Suppose that you have a lot of data.
Yeah.
So, and you could use, for example, the least square. So what would be the advantage of using the neural network in this case?
When you tell me least squares, I think of a cost function.
Yeah.
But you can use, if you are in a regression problem, you can use your neural network with least squares, no?
Yes. So
I am like I put here that I try to obtain the derivative with respect to a cross entropy, which is applied for classification. But in the case of a regression, you take mean squares, and then you compare the observations with the predictions. The prediction is just a neural net where the final activation function is the trivial one, so f of a is equal to a, and all these expressions are much more simpler.
Yeah. So the question is something like, I mean, for which kind of problems is just much more efficient using a neural network rather than standard methods in regression? I don't know.
Well, in regression, if your function is very complicated, then you will obtain better results with a neural network. If your function is like wiggly, quite, or it is a combination of components, like in signal and background, you may have one component behave in some way, and suddenly you have some other behavior, and then you go back to the previous behavior, things like this. Then
so when you have like complicated function and limited number of data, something like this.
Yeah, exactly. So the idea here is that for the type of models that we were discussing at the beginning of these lectures. So, for example, this basis model, or the polynomial, or even replace not the phi's by the exponents of x. So this is not a polynomial at all, but it may be just this phi's may be a catalog of nonlinear functions, let's say. This also gives you some flexibility, of course, because for every point you are saying that this is a linear combination of nonlinear functions. So the idea is roughly the same, but in practice, these linear basis functions, they should be less flexible than the neural net. And the idea is all going to the universal approximation theorem that applies to neural net. Yeah. So I haven't seen like efforts towards approximating any linear function with a linear basis function. But there are limitations of these linear basis functions. For example, you need to specify beforehand what is the catalog of your linear function. And are these polynomials, or are these trigonometric functions, or something? Okay, you may say, okay, I will cure myself. So I will just start with a very, very large catalog of linear functions, of nonlinear functions. But if you do this, then your problem becomes a little bit complicated. I don't know. So it is something that I probably I'm not able to give you a deeper answer than that. But seems to be that in practice, when you seem to have a very complicated data, you go to a neural net and it does the job.
So under which conditions would you have the same result than with the standard method, like having a lot of data, for example?
When you say standard method, what do you
mean? I mean, like what you were showing about the Bayesian or standard regression, like minimizing the chi-square.
Yeah, so note that they can embed my neural network in a Bayesian approach. So
yeah.
So what I have been showing so far for regression is this linear model. If this is what you're referring to, standard method or standard models, then I don't know. I mean, try approximating depending on your data set. So I don't know if I can answer before looking at the data set. It is true that I mean, and this is quite unfortunate what is happening now in the community, not in the research like a physicist community, but in people applying machine learning to some problems. What is happening now is that they go to very complicated models like convolutional networks before trying other simpler models that may give you an acceptable performance. So this is something unfortunate, because then you lose this Occam pressure driving principle that that you may use to follow in physics, let's say, right? So when I discuss with my data scientist colleagues, they just say, okay, this problem, let's just try this beast. This is a huge network. This will do the job. And they say, okay, but why not to try a polynomial first? Okay. So I am always in the back of my mind, I am always going from simpler to the more complicated ones, because this is the way my physicist mind is working. But it turns out that that you have these techniques of regularization, etc., that tells you, okay, now you choose a beast and a convolutional deep network. This beast with the correct regularization will work in the sense of not giving you overfitting, and will do the job of estimating something, some function for you. Yeah, but I prefer to go from the spherical cow to more complicated models. Yeah.
Okay, thanks. So it would be interesting to define like the set of problems where it is convenient to use the neural network.
Well, we have seen this in the first lecture. So for problems, for example, if you're in collider physics and you want to estimate the behavior of your events, then you better go to a neural network, because this is too complicated for other standard models, for standard methods, I'm saying.
Okay.
So
thank
in
you.
collider physics, this applies. In astrophysics, which I am working with, it also applies in the sense that there you may have a noisy sky or noisy emissions, let's say. So probably this is too complicated for a simpler model. So you need to go to a neural net. And so in general, when your system is very complicated, it is a good idea to go to a neural net.
Okay, thanks.
Okay, any other question? Okay, so if there is no question so far, we can close today's session, and we continue when on Thursday probably with the hands-on of
Yes,
neural
on
net.
Thursday.
Okay, thanks a lot then, and then see you on Thursday.
See ya.
Bye bye.
Bye bye.